Alright, welcome back to probability lesson 2.4. So last time we talked about the correlation, the idea of correlation, and this time we're going to continue that idea. We're going to talk about calculating that correlation, because there is a value associated with it, and it's a pretty interesting way to calculate. Maybe a little complicated, but we'll get through it nonetheless. Let's go ahead and go forward. Today's objectives here, we've got 3 of them, but I would say maybe the 2 that are the second ones about the properties of correlation and how outliers influence correlation are a little more important. The first objective is just seeing how statisticians and the like calculate this correlation value. Using these 3 features that we kind of already have talked about: mean, standard deviation, and z-scores. So we'll definitely take a look at doing that. I'll show you a couple of resources you can use to help you out on that one, because reality is most people don't do this by hand. Learning and apply the properties of correlation. We're going to talk a bit about what correlation, the value, is doing and how it works with all these other things that we talked about the explanatory variables, response variables, all that other good stuff, and all that stuff and more. And then how about the outliers influencing correlation? Well, we're going to be looking at outliers and seeing if they affect our correlation value. So let's get started. So here is a little brief instruction on how to calculate the correlation, which, remember, is basically measuring strength and direction in your scatter plot. So for quantitative variables, it's measuring strength and direction. So the first step to doing this, is going to be, maybe stuff from last chapter you may not remember too well, but finding the mean of whatever data you're looking at, finding the standard deviation of the data you're looking at, and then finding each individual's z-score. Each individual z-score. So for example, I'm going to go ahead and compare the feet length and height of 6 individuals. Actually they're high school seniors, I forgot to mention that here, but high school seniors, 6 of them, and I measured their height and feet length in centimeters. Let's go ahead and move over to how I'm going to find the mean, standard deviation, and z-scores for the feet, of these seniors. Alright, so here I am with Google Sheets. Of course, you guys all have a Google account, so Sheets should be easy to pull up whenever you're working on. And please use Google Sheets or something to help you figure out these mean, standard deviation, z-score stuff, because I don't want you spending your whole time on this when the real meat is supposed to be about correlation. So let's go ahead and get to it. I've copied down the feet lengths from the problem, so let's just hop to it. Now, if you're looking for averaging, you don't want to do the work. You just type in equals average. And you're going to go from here, D2 to D7, it looks like, in my data anyway. So mean of this data here is 26, and you can also do it by hand. There's only 6 of them, but the standard deviation you definitely don't want to do by hand. So I'm going to put an stdev, that's our standard deviation call, and I'm going to kind of scroll down and do this way, for those of you who are wondering, and it actually pops up a preview for me. Nice. So when I click enter, that's what it's going to give me, right? Now it's pretty long. I'm going to round it to about 3.95, 2 decimal places. And that should be what I get for this foot length variable. Now the last one is z-scores. Z-scores. Now there isn't actually a call for this function, for this type of procedure in Sheets, not that I know of anyway. So we'll just have to recall what that function, that formula is. Remember, it's your argument, which in this case is going to be D2, minus your mean, which is 26, divided by my standard deviation, which in this case is 3.95. Now, I use this way because if I try to put it in with these as my arguments, then it will try to shuffle it down. I'm going to use these numbers to give me my z-score. So the first z-score is about negative 0.76, etc., etc. So I'm going to drag this down, a very neat feature you can do there, and then it'll pop up all the z-scores for your individual observations. And I'm going to go ahead and just format this here. Let's see, where's my formatting? I'm going to format it to be decreased decimal places. There we go. I'm going to go with 2 decimal places again, I think. That's probably about right. All right, you can always use that function over here in the top. I was looking in the wrong place. But those are my z-scores for feet length, okay? And we'll figure out what to do with them after I let you try this with the other set, the height. All right, so I'm back here with the correlation slide with both the height and the feet length, but I want you guys to follow the steps I just did for feet length using the heights instead, okay? You can use sheets, okay? If you have another site you'd like to use, feel free to use that, but I'm going to give you a little bit. Try to find it out, and you'll check back here for the answers when you're finished. All right, and here are the answers, okay? I put height for you guys up top so you can check them right there, but feet is everything I found below when I was doing it in my own little window there, and they all pretty much match up, so I think it's pretty accurate, all right? Now, I'm going to go ahead and move on from here to talk about how to finish this off, how to get my correlation actually, because what I've found so far is stuff we've already talked about, z-score, standard deviation, mean, all that other good stuff. But here is the new process. So don't blink and you'll miss it. From here, a couple more steps, we're going to multiply all of the z-scores together, okay? All of the z-scores together per individual. So, for example, in this column, I'm going to multiply these together. For this column, I'm going to multiply these together, and so on and so on and so on. Okay. Once I've done all that, I'm going to add all the products and divide by n minus 1, okay, which in this case is going to be 6 minus 1, or 5. Right? So let me head back over to the sheets, because I definitely don't want to be doing this by hand, I'm sure. You don't want to multiply all this by hand either. You got a calculator, hopefully. All right, so I've updated the sheet with all your heights. Okay, you should be able to check that before you moved on. And so I'm going to go ahead and start multiplying these out. So this is going to be the argument here multiplied by our argument here. Okay, we're corresponding them to each other. I put them in order, so that should be correct. And then I'm just going to drag it down and see what happens for my next 6 slots. Okay, cool beans. This uses G3 and G10. Here's G10, so that should work as planned. Let me go ahead and shorten these again to a couple decimal spots only, so it's not super in the way. This one missed it. Okay, and then again, once you've gotten all of those, you're actually going to add them all up. Okay, so equals sum, right? I2 to I7, that is correct here. That's what I'm looking for. 420, isn't that a convenient number? And then finally, I'm going to take my sum and I'm going to divide it by n minus 1, which in this case is 5, okay, for a total of 0.84062, so on and so forth. And I'm going to go ahead and truncate that to 2 decimals as well. Okay, so this number right here, I'm going to go ahead and make a big, fat, and bold. Okay, maybe make it a nice, vibrant red color. Okay, this number right here is our correlation coefficient. Our correlation coefficient. Let me go ahead and just write it out here. Correlation coefficient, okay, which you can also call R, okay, is usually called that anyway. And that tells us the correlation between our two variables here, our foot length and our height. Okay. Whew, thanks for sticking with me and figuring out how to calculate correlation. Now let's head back to the PowerPoint and see where we stand. All right, welcome back. So we're back. We have the correlation, but what's it mean? Okay, what's it mean? This is something you should be able to tell me based on your understanding of correlation so far. But we found from our example that the correlation between height and foot length was 0.84. So please take a moment to interpret that value in the context of the problem. All right, hopefully you took a couple minutes to think about that, okay? In the red is what I was looking for, okay? Basically, if you had above average foot length in that student's population, then you were typically above average height, and vice versa, okay? Or vice versa if you wanted to put height as your explanatory variable, etc. This correlation shows a strong positive association between them, okay? Measuring strength and direction. That's what correlation does. So please make sure you kind of have this idea of what correlation means down. Okay, so we move forward. You don't have to worry too much about talking about what's it mean, right? All right, so before we move on to the next section, which is talking about the properties, okay, I'm going to show you this neat little site that will help save you a lot of time on the IP. If you don't want to use sheets, you feel like it's a lot of work to do, Okay, but do know that you will have to go through that. You can't use this on a test, etc. But it can help you see the idea behind the computer doing it. But this is Pearson's official correlation coefficient calculator. So if this stuff interests you, to take a look at data and stuff, okay, you can actually plug in your x value, which is whatever you're talking about. In this case, this is my foot length, and y values, which in this case is my height of the students. Make sure they're attached to the right numbers in order, okay? And then you can just click calculate R, and it will give you all of the points. Okay, it will give you all of the stuff. Okay, so if you click this, okay, the value of R, okay, the value of R is 0.8405. So it's pretty close to what I got on Sheets. Okay, I know Sheets did a couple little rounding things, and I did a little rounding myself, so of course it's not going to be exact. But this Pearson correlation coefficient calculator does the same thing that Sheets would do, except it cuts out all that intermediate stuff. Okay, cuts out all that intermediate stuff. So you want to go ahead and scroll down. This actually has a scatter plot to showcase how that looks. Okay, how that looks here. Although I think it scales based off of from 0, so this is going to look a little weird compared to our scatter plot that doesn't label them either. Okay. But here you can also tell what their mean is, right? Mean of x, mean of y. Okay. And then it doesn't show standard deviation, so be careful there. But it does show you the little process, the little formula that I haven't mentioned because I feel like it will just confuse you guys. Okay. If you want to take a look at this site to help you figure out correlation and calculating that, that can definitely be something you do in your downtime. Okay. It also even has like a little blurb at the bottom telling you the interpretation. Strong positive correlation, which means that high X scores go with high Y scores and vice versa, right? Okay. Back to the video. We got 3 properties I want to talk about real quick, although the first one is definitely the most important. Okay, those being that correlation does not distinguish between explanatory and response variables, different measurements of the same data don't change the value of correlation, and correlation is a standardized value with no units. Those are the 3 properties we're going to talk about here, but the first one I'm going to talk about at length. So let's give it a go. So first of all, it doesn't distinguish between explanatory and response variables. Okay, so if you've been wondering so far that what's the point of determining explanatory and response variables, at least when correlation is involved, there isn't actually, okay. But this does support the idea, okay, that we've talked about before, that correlation does not equal causation. Association does not mean that one thing causes the other, right? All right, but if you want to think about it mathematically, you think a little better about it mathematically, it's kind of like changing the order in which you multiply your variables' z-scores together. Okay, and remember that multiplication is commutative, which means order doesn't matter. Order does not matter. Okay, and that's this whole idea that pretty much allows correlation, that is, to not distinguish between the 2 variable types. Okay. So here's a question for you real quick. Suppose I found the correlation between heights of a roller coaster attractions and top speeds using height as the explanatory variable. Would the correlation change if I use top speed as the explanatory variable? Go ahead and answer on the Edpuzzle. All right. Of course, the answer is no there. Okay, so you will not be changing based on that because, again, it doesn't distinguish between those 2 things. So, of course, if you try to switch them up, it won't affect the correlation at all. Moving right along, we have the other 2 properties, which are kind of tied together, so I put them in the same slide. Okay. Talking about different measurements of the same data do not change the value of the correlation. So basically, just like the first point, let's say I measured the feet lengths and heights in different units, let's say inches, or even if I combined inches, centimeters, feet, okay, etc., the correlation would still be the same, okay? And this is because correlation is a standardized value and has no units, okay? So as we continue to talk about more and more concepts, we'll continue to talk about standardization and what that really means, okay, when mentioning these ideas that we've mentioned so far, like standard deviation, z-scores, and correlation, okay? We're going to talk about more, of course, but those are the ones we know so far. All right. So here's a question here. Right before we get to the last part of our lesson here. When describing the effect of outliers on other measurements like mean and standard deviation, what term did we use to describe them? You had a choice between resistant or not resistant. Give you a sec to think about that. Recall it from your previous notes. All right, and of course the answer here is not resistant. Okay, mean and standard deviation are not resistant, while median, okay, and all your quartiles are resistant. So there's that idea coming back at us. Maybe you guys forgot all about the word resistant, but here we are again. Okay, that's a very important term to figure out. Now let's talk about outliers and correlation. Okay. Just like the measurements we use to find correlation, which is standard deviation and mean, the correlation itself is not resistant to the pull of outliers. So let's see what that means in the graph. Okay, so it's going to be a little more in terms of this. Here's our example comparing cost and battery life, okay, of computers. So, can you find any outliers in the following scatter plot? I'll give you a sec to look at it. All right, I'm back. I did also move it over a little bit so you guys actually see the whole picture. I had it moved over from before. But if you answered these two dots over here were the outliers, okay, you were totally correct, okay, because they look way further out than all the other points. You might say that some of these might look like outliers, but I think definitely these two over here. So, the next question to follow up on that, how would you describe the correlation if you didn't include the outliers? Let's say you don't have those. How would you describe your strength of association and direction, okay, of the scatter plot? I'll give you guys another second to do that. Alrighty, and if you said something along the lines of, okay, a line like this, so positive correlation, and then a moderate association. So not super strong, but not super weak. That's probably about right. Now, if you show something other than moderate, that's totally up to your interpretation, right? Let's move on then. I'm talking about this final, blurb about talking about it with the outliers, okay? So if you're talking about a moderate association, you might be thinking about a value around 0.5, 0.4-ish, okay? But if we were to calculate the correlation with outliers, of course I didn't do that, okay, because we got running low on time, but if you include these outliers, they definitely have z-scores that are much lower, okay, or much more influential than all the other z-scores. So with these being lower than your line of best fit here, this will probably send the correlation number to be closer to 0 or possibly even negative, okay, in our case. So, but we're definitely at a positive correlation, a decently strong association, which makes it closer to 1. All right. And that's basically what I wanted to show you about the outliers effect on correlation today. Now, if you guys need to go back and look at the objectives for today, I want you guys to check it out and see if you're ready for the in-class practice. Please take a look at that, and I'll see you guys in class for this lesson.